One of the questions on the test is taking an expression that looks like this and converting it into a form where we can use the geometric series to come up with the infinite series, the geometric infinite series, to come up with the infinite series to represent this. And I presented a method in the review and in class, and I'm like, there's got to be a better way. So I came up with a better way. So I was going to show you how to do that today. So this comes down to what you're trying to do is use this fact. So we know that a series that looks like this well, there's two things that happen. One is it converges if R is less than 1. And it also converges to A divided by 1 minus R. So the idea here is to take the original expression and make it so that it looks like that. And then we can go backwards using this side and go back to deducing what the geometric series that would give us this result. So the best way to do this is to, let me make sure I use the right terminology here. Really what we want is A divided by 1 minus BX. So normally R when we first introduced it was a number, 3/4, 1/2, 2.7. But in this case, what we're going to try to do is make R some constant times X. And therefore it becomes an infinite series as a function of X instead of just for one value, essentially one value of X. Now this is true if we're centering the series around x equals 0, which we are doing for this case. On the back side, we'll do it around for some centering around some value of c other than 0. So if I asked you to do it around c equals 0, we use this form. Because essentially we have x minus, you can think of this as, don't write this down because you'll see why this is true on the next page, but it's 1 minus b times x minus 0. So by subtracting 0, we're going around c equals 0, and if it's any other value than 0, we're going to do x minus whatever that number is. Okay, so don't write that down. So the way we solve a and b in this case is you set these two equal to each other. So that means you're going to cross multiply. So we're going to take 3 times 1 minus bx is equal to a times 4 minus 2x. So I'm taking this times that and this times that. And I'm going to let you do the rest of it. Solve for a and b. Now you're saying, okay, give me a little help there. What does Austin Powers say? Give me a bone or something. Right? Give me a bone. So what you're going to do is you're going to multiply it out, and you'll have terms that involve x. So you'll set those coefficients equal to each other. And then you have terms that don't involve x, and you'll set those equal to each other. So you'll end up with two equations and two unknowns. So we'll have negative 3b and negative 3bx and 4a, well, negative 2ax. So then you just set the coefficients equal to each other, just like we did with partial fractions. So just think of partial fractions. When you're trying to solve for those coefficients, you multiply the whole thing out and you say, let me set the coefficients for the x part equal to each other and the coefficients for the constant parts equal to each other, and then figure out what those constants are. I guess the other option is you could pick some value of x and two values of x, and you'd have two equations and two unknowns. But it's probably easier just to do it the other way. So go ahead and multiply this out. I'll do it in a second, but you try it. So just multiply these, expand those out, and then you'll have 3 is equal to 4a. So you'll be able, in this case, you'll be able to solve for a first, and then once you have a, you can solve for b using the second equation, the one that involves the x variable. So those are your two equations. And like I said, you can solve for a from the second equation, plug back into the first equation, solve for b. So you should get a is 3/4 and b is 1/2. So I plugged a equal 3/4 in the first equation. 2/4 is 1/2, so that's what I did there to simplify. The negatives cancel out, divide both sides by 3, and it simplifies down to 1/2. So what that means is now I can go back and I can say that 3 divided by 4 minus 2x is equal to negative 3/2 divided by 1 minus 1/2 x. So I plug it back into this equation. And now that's of the form a over 1 minus r. So from that I can say the a that I'm going to use here is negative 3/2, and r is going to be negative 1/2 x. So this is a, and this not with the negative sign. So I should be positive. Well, pardon me? It should be 3/4. I don't know why I did that. Thank you. 3/4, and it, okay, so that's 3/4, and it shouldn't be why did I put negative? I don't know why I keep thinking that, sorry. I think I'm thinking ahead to the next problem, so my subconscious is crazy here. Okay, let's try it again. So it's a is 3/4, and that's positive 1/2. So now what I can say is that I can represent 3 over 4 minus 2x is equal to the summation from n equals 0 to infinity of 3/4 times 1/2 x to the n power. And convergence, the convergence criteria for the geometric series test is that r has to be less than 1. So in our case, that means that 1/2 x has to be less than 1, and actually it's the absolute value. So the absolute value of r has to be less than 1. Let me fix that too over here. So that means that in this case, we can rewrite it as this kind of inequality. And if you multiply both sides by 2, you get -2. So this particular series representation of the original equation is converges between -2 and +2. But outside of that, it doesn't converge. I don't think it includes the endpoints. I don't think we. I'm not sure. I don't think we evaluate the endpoints, but I'm not 100% sure of that. But I'm not going to ask you in the problem on the test. I'm not going to ask you the question about convergence. But I thought about that last night in my subconscious. Okay, so let's turn the page over. So it's the same equation, but we're going to center it around c equals 3, or x equals 3. So c equals 3. So the difference in how we approach this, we still want it to be a over 1 minus r. So we're going to have a over 1 minus b times x minus 3. So because we're centering around x equals 3, we want r to be a function of x minus 3. So when x equals 3, you're going to end up with that term going to 0. But as far as solving for a and b, it's the same procedure. You're going to cross multiply the first and the last expression. So we'll have 3 times 1 minus b times x minus 3 is equal to a times 4 minus 2x. Solve for a and b. And the same approach works. The only difference is that you won't be able to, you'll have each equation or each expression, the one involving x and the one involving the constants, will have both a and b. So you'll have to use substitution to solve for either a or b, and then go back and solve for the one you haven't solved for previously. So that's the only difference. So multiply that whole thing out. Set the terms involving the constants equal to each other, and the coefficients of the terms involving the variables, the variable x. Set those equal to each other and did the algebra for that. And you'll see why I accidentally wrote 3/2, because that was what the answer is for the second one. That is. So those are the two equations. If you don't get what I did here, I just took 3 times 1, 3 times b times x with a negative sign once. So that's where I got negative 3bx, and then 3 times negative b times negative 3. So negative 3 times negative 3 is positive 9 times b. That's how I did the. You might have had one additional step in there. So what I would well, I don't think it really makes any difference. You can either solve this one for A or B, this one for A or B, and then substitute it into the other equation. So what did I use? Well, I did the opposite when I was working through it. So I'll just be consistent. But you might pick a different approach here. What'd you get? Yeah, something's wrong. Yep, that's good. Yep, B's right. Have you got an answer yet? Yep, good job. So I decided to, because I did it on my paper when I did it yesterday, I solved the first equation for B. You could solve for A. It doesn't really matter. So you solve for first equation for B, you plug into the second equation. So we're using substitution. 9 divided by 3 is 6. 9 divided by 3 is 3. 3 times 2 is 6. 4 minus 6 is negative 2. Divide by negative 2, you get negative 3 halves for A, and then B is 2/3 times A, so you get 2/3 times negative 3 halves, which is negative 1. So those are the coefficients that you come out with. So now what we can do is we can go back and rewrite. Let me go up here, add a page. So what we can do is we're taking this part, so we have 3 over 4 minus 2x is equal to A is negative 3 halves and B is negative 1. Now I left the negative sign here because that's supposed to be A over 1 minus B. 1 minus R. So in this case, A is negative 3 halves, and R is equal to negative x minus 3. So what we said is the summation from n equals 0 to infinity is A times R to the n, And so using the values for A and R, we have negative 3/2 times negative x minus 3 to the n power. Now, you might have stopped there, and I probably would be okay with that, but I'm just going to show you something. The negative 3/2 stays the same, but what we would do is we'd take the negative sign here and make that negative 1 to the n times x minus 3 to the n. Because that's more like an alternating series, because it has the negative part. Whereas in this previous problem, we had both positive stuff. So when we did the series expansion, they were both positive. So that looks more kind of like a more traditional geometric series. But you can have negative numbers in there. It doesn't really matter. Anyway, those are the two series. Let's look at convergence. So convergence would be the absolute value of 1 minus x minus 3 has to be less than 1. And so those are absolute values. So the negative sign just drops out because it's the absolute value, so I can just say that is true. So we would have, we can then change it to this kind of inequality, and then we'd add 3 to both sides, so you'd say it's good between x equals 2 and 4. So this, when you're centering it around something other than x equals 0, the interval of convergence is tighter. The radius is smaller. If we went back to the previous problem, you're saying the interval was between negative 2 and positive 2. So that went plus or minus 2, whereas this one just went plus or minus 1. And I found that out the hard way yesterday. I said, it'd be interesting to see if this thing actually works or not. So I did an Excel spreadsheet to evaluate these two functions. So it's this one right there. So what I did was I evaluated the first series, the one on the front page, at x equals 1, which is within the interval of convergence. It goes from minus 2 to plus 2. So plus 1 works. And I know I can evaluate the function. I just plug in x equals 1 into the equation, and I would get 1.5. So what I've done is, this is a sub n, which is going to be 3/4 times 1/2 times n, or times x. So this is the x value, 1/2 x to the n power. So when you take 3/4 times 1/2 times 1 to the 0 power, you just get 3/4. And the second term in the series is 0.375, and the third term is 0.1875. And to get the actual, these are the partial sums of the series. You keep adding these up, and lo and behold, if you get up to about 14 terms, it comes out to pretty close to 1.5. So you can have faith that if I take an infinite number of terms, then I will get to 1.5. Now when I did this one, I originally evaluated it at 4, and it didn't work. It didn't converge. I'm thinking, why does this one converge when it's only 1 unit away from where I centered the series, whereas this one didn't? Well, if you look at the convergence criteria, you can see why. So I evaluated it at 3.9, which is within that interval. And if I evaluate it at 3.9, I get -1 for the value of that expression. And the series representation You can see how now it's an alternating series instead of a non-alternating series. But the first term in the series is negative 1.5, and then you add 0.75, subtract 0.375, add 0.1875. And ultimately you get down here and you can see it's approaching negative 1. So they do work. But if I did something just slightly out of, let me just show you, if I put in 4, so instead of, actually this is 3.5. Did I say 3.9? Should have been 3.5. So that's still within the, let me fix that so next time I don't make a mistake. Okay, it was at 3.5, which is still within the interval. But if I evaluated it at 4 instead, what you see, it just bounces back and forth. If I evaluated it at 3.9, it's converging, but not too quickly. It's converging pretty slowly. So the closer I get to where I centered this thing, if I go to 3.2, then it converges very quickly. You can see right there. So the further you get away from the center point, the more slowly it converges, but it will converge. But if you do it anything at 4 or above, if I did 4.1, it's going to diverge. You can see how the number is just going to keep getting bigger. So anyway, it did work, so it was pretty cool. At least I thought so. So let me just give you a hint for the test. It's going to be like this. Okay, I'm going to give you an expression that's centered around something other than x equals 0. So make sure you know how to do this kind of problem. I'm going to let you keep those handouts. You can turn them in on Thursday when you take the test, and so I can give you a credit for being here today to do that. But just make sure you understand what's going on there. Yes. Yes. Yeah. So it's x minus c. So if c is positive, it's going to be x minus 3. If it's negative, you'd have x minus the negative 3, which would be plus 3. Yeah. So we're going to go back to section 10.2 now. So we're talking about parametric equations. So the last thing we were talking about was using this form for calculating the parametric equation for a line in 2 dimensions given 2 points, x1, y1, and x2, y2. So let's go ahead and try this. All you have to do is basically just plug them into the equation and simplify. So you want x equals some expression involving constants and t, so you can just do the algebra x2 minus x1 and y2 minus y1, and then simplify it using the 2 points that are on the right hand side, which are 1, 4, and 5, negative 2. We're doing algebra today. So Okay, you're like, there must be some trick, right? He's trying to trick us. It's too easy. No, I'm not trying to trick you. So you just plug the numbers in. 5 minus 1 is 4. Negative 2 minus 4 is negative 6. So that's it. While you were, I put up, the nice thing about the parametric form is if you had a line in three-dimensional space, then the parametric equation for the z coordinate would just be z1 plus t times z2 minus z1. So it's easily expanded to 3 dimensions. Okay. Now it turns out that you can have more than one set of parametric equations defining a line. So if I had chosen this one as x1, y1, and this is x2, y2, I could end up with different expressions as far as the parametric equations. The trajectory would still be the same. And it's not just true for lines. You can have multiple parametric equations defining the same curve. So that's just okay. Now these are we didn't in section 10.1 we talked about the general form of the equations for circles and ellipses, and these are the parametric form for those same shapes. So a circle, instead of x squared plus y squared equals r squared, it's going to be x is equal to h, which is the x coordinate of the center of the circle, plus r, which is the radius of the circle, times the cosine of theta, where theta, and we're using theta as the parameter, not t, just because we think of angles or rotating, making something where you're building something as you rotate around as theta. You could use x, you could use t, you could use theta. You couldn't use x because that's the coordinate, but you could use any variable other than x or y. So there's no significance to that. And y is equal to k plus r sine theta, where k is the y coordinate of the center of the circle, and r is the radius of the circle. And let's just, and if you did that on your calculator, you would get a circle. We did that the other day, except we didn't have h and k. But let me just pull up my graphing program that I used the other day and demonstrate how it works. So if we go to a two-dimensional graph and we go to parametric equations, and so if I put 5, what was the equation? I've already forgotten what it is. Yeah. So it's 5 plus, actually let's use 0.5, plus 1.2 cosine theta. In this case, I'm going to use t because that's the variable that they use. And if I did minus 0.5 plus 1.2 sine theta, sine t. So the difference, I've got these two numbers have the same value, so it becomes a circle. And the center is going to be at positive 0.5 x and negative 0.5 y, and I plot it. And you're like, whoa, what happened? That doesn't look like a circle to me. Okay, so the problem I did was you also have to specify the value of the parameter, and I only went from 0 to 1. So if I went from 0 to 6.28, which is about 2 pi, oh my gosh, what happened there? That wasn't what I was expecting. Oh, it's because I forgot to edit the formula. It used this formula, not one I just gave it. So let me start all over again. So we'll close that. Okay, so we go back here, parametric equations, 0.5 plus 1.2 cosine t minus 0.5 plus 1.2 sine t. My parameter goes from 0 to 2 pi. And there's there's my circle. So it does actually work. Okay, so that's the equation. That's a parametric equation for a circle. The parametric equation for an ellipse is x plus h times a cosine theta, and y is equal to k plus b sine theta. So again, the center of the ellipse is at h comma k, and a is the length of the axis in the x direction. The major axis, well, major depends upon whether a is bigger than b, but in this case they're not the same. So a circle has a equal to b, which is equal to r, whereas an ellipse, they can be different. And the more different they are, the more elongated your ellipse is. Now for a hyperbola, you might have thought to use negative signs, but you don't use negative signs. You use the secant and the tangent, which is kind of interesting because we've been dealing with that in calculus. You know, the cosine and sine go together and the secant and tangent go together. So hyperbola is h plus a secant theta, and y is equal to k plus b tangent theta. Again, a and b determine how narrow or wide it is. And the parameter is theta, which goes, all of these theta goes between 0 and 2 pi to get one complete curve. So let's look at this one, the hyperbola. So 2 dimensions, parametric equation. So if we did 1 plus, let's switch first, secant or tangent? Secant. Okay, 1 plus 2 secant t, and g was -1 plus 3 tangent t. And we'll go between t equals 0 and t equals 2 pi approximately. And nothing happened. What happened? What's that? Oh, did I? Okay. Yeah. Okay. Yeah. Something that would do it. That would do it. Okay. Let's try it again. I don't know if it's exactly the same equation. Doesn't really matter. I just want to put something in there that uses secant and tangent. So we'll do -1 plus 3 tangent theta. Try not to push cancel. 3.29. -1. So the center is going to be at +1 x, -1 y, and that looks about right. Okay. So there we go. So that's your hyperbola. So you can see if you drew a vertical line here at +3, it would just touch this hyperbola here and at -1. That's because the center of the hyperbola is right there. So it's symmetric around that point. And so this distance is 2. That distance is 2. Now the other distance, you don't see it in this picture, but you'd go 3 units away from the center, and then you draw a rectangle, and you draw diagonal lines through the opposite corners of the rectangle, and that would provide you with the asymptotes for this particular hyperbola. Now, I'm just thinking about this. I wonder, how do you get the hyperbola to go to the other direction? I think you actually may change. Let's see what, because in this case it's going like this. What if you want it to go like that? I think you would switch which one had the secant and which one had the tangent, I believe. I don't think it has to do with negative signs, but let's just try it. Let's see what happens if I put a negative sign in there. So if I have 1 plus secant, let's put a negative. I don't know what's going to happen. Probably it's not going to work, but let's try it. Anyway, that's the nice thing about, I can't break anything. So if we make one of them negative, you get a straight line. Oh, that's cool, kind of interesting. So apparently that doesn't work. So the other option is I can switch. If I did 1 plus tangent, let's say 3 tangent. So I put the tangent with the x coordinate, and I put the secant with the y coordinate. Let's see what that looks like. Yeah, so there you can see that changes. So that must be the right thing to do. So if you wanted to change the orientation, then you could do that. And let's just put this on one page. Yeah, so this is just another example. If you have an ellipse with a center at x equals 3, y equals 2, with a equal to 5 and b equal to 3, this would be the rectangular representation of the ellipse, and this would be the parametric representation of the ellipse. So this is called the Witch of Agnesy. Anybody ever heard of that before? Sounds spooky, right? Must be something. Let's see what happens. We'll see if anything spooky happens. So it's 2 cotangent. So the 2 cotangent theta is x, and y is equal to 2 sine squared theta. 2 sine of theta squared. And we'll go from 0 to 2 pi again. Doesn't look too spooky, right? Okay, so let's look it up on the internet. So it's kind of an interesting concept, just figuring out what the heck they're talking about. Starting with a fixed circle, a point O on the circle is chosen. Okay. For any point A on the circle, the secant line OA is drawn. Okay. So remember, a secant line is just a line connecting 2 points on a circle. So, okay, it's drawn. The point M is diametrically opposed to O. Oh, there we go. Okay, that's M. The line OA intersects the tangent of M at point N. Okay, that's the N up there. The line parallel to OM, this one here, the line parallel to OM through N and the line perpendicular to OM through A intersect at P. Okay, so this line, parallel line, intersects this line, I think something like that, at P. As the point A is varied, the path of P is the Witch of Agnesy. So that's this curve. So if you repeat this process for different positions of A, you get the curve that looks like that. And you can define it parametrically. That doesn't look too spooky to me. Anyway, it's the reason it's named after a Italian mathematician. I think it was probably because the men didn't like her because she was a mathematician, so she must be a witch or something. It's kind of pathetic. She was the first woman to write a mathematics handbook and the first woman appointed as a mathematics professor at the university. That was the 1700s. So why does it say she was the witch? Let's see. Witch. Oh, no, it doesn't have to do with her at all. Called the curve in Latin suggested the term blah, 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 possibly as a pun. Yeah, so it really has nothing. It's kind of a weird explanation, but anyway, it's nothing to do with her, but I always thought they were trying to be mean to her or something. So here's the last word here, the last word with Steve Nicholson. So lines in three-dimensional space are most easily represented using parametric equations. That's probably one of the places that you'll see the most in math. Some complex figures are more easily drawn using parametric equations. So like the witch, coming up with a rectangular version of that equation may be difficult, especially if you have things like spirals. You saw that thing that I accidentally drew because I just took the default. You know, if I go back to my graphing program and I close this and I go and pick out the standard default equation that they put in here, which is 3 cosine of 3t and 3 sine of 4t, and I do that and I go from 0 to 1. Actually, I don't want to do that. I want to go from, let's try it again. We're going to go from 0 to 2 pi, 6.29. You plot that and you get that cool picture, right? So you can't do that with x versus y. And also in physics, you know, those are the trajectories of the particle, are parametric equations. It's also where you're interested in not just the path, but how fast something moves with respect to the parameter. So in physics, you could have the same, I could take the same path here like this and come around like that, or I could go, okay, same trajectory, right? But the second one was more exciting. Maybe that much more exciting. Okay, at least I didn't fall. And also, you know, when we, if we have the vectors, the components of the vectors defined by these parametric equations, we can take the derivative of the position value with respect to time, and that gives us velocity and acceleration. So there are quite a few cases where parametric equations are useful. And did I already sign this or not? I can't remember. Oh, yeah, okay. So that's our introduction to parametric equations. The next section is about the calculus of parametric equations. And really all we're doing, we're only looking at derivatives in this case. And the question we have is, given the parametric form of an equation for a curve, what is the slope of the tangent line to that curve? So we're doing the same thing. We want to find out what dy dx is, but we want to do it through expressions that aren't y versus x, but y versus theta or y versus t and x versus t. It's not really it's not that hard. So and where does that come into play? When we're doing derivatives, so that's the one I just mentioned. Also, if you go back to Chapter 7, Section 4, when we talked about calculating arc lengths and surface areas of the area of rotation of surfaces, sometimes the surfaces are more easily defined in terms of parametric equations, and the areas and lengths are more easily calculated. So here is the result. So what we're trying to do is find, in this case, we're just looking at the derivative. So the derivative, which is the slope of the tangent line to the curve, x versus y versus x, is dy dx. So what we do is we take dy dt divided by dy dx. And just from an algebra standpoint, if we were looking at the differential form, the dt's cancel out. So all we have to, that's it, okay? So if we have two equations for one equation for x and one equation for y, each one a function of t, then we take the derivatives of those equations with respect to t and just divide the two. The result, dy dt and dx dt, that'll give us dy dx. And if you want to take the second derivative, so you want to know something about the curvature and the concavity, d squared y dx squared, you take the derivative, first you take dy dx using the previous step, and then you take the derivative of that with respect to t, because this will end up, this dy dx expression will be a function of t. So this is a function of t. So then you just take the derivative again, and then you divide by dx dt, which you've already done here anyway. So we'll have this already done. We get this part from here, and then we just take the derivative again. That's how you get the second derivative. So let me just do this example. This is a parametric equation. X equals the square root of t, and y equals 3t minus 1. So to find dy dx, the slope of the tangent line, dy dx, not dy dt. So dy dx is dy dt divided by dx dt. So let's just do those separately here. Dy dt would be equal to the derivative with respect to time of 3t minus 1, because that's what y is. So that's equal to 3. So the variable now is t instead of x or y. So the derivative of 3t is just 3. And then if you do dx dt, dx dt is the derivative with respect to t, not time, of t to the 1/2 power, which is going to be equal to 1/2 t to the minus 1/2 power, or 1 over 2 square root of t. So I move this to the denominator, rewrite it. So dy dx is just equal to 3 divided by 1 over 2 square root of t. Okay, and then I could, this is in the denominator, so I could take the reciprocal. So you'd end up with 6 times the square root of t if you simplify it. And that's the answer. So the slope of the tangent line to this curve as a function of t is 6 times the square root of t. And we'll come back to this. What we'll do is we'll use eliminating the parameter to rewrite this as y versus x, and we'll show that it's the same answer. It's basically the same result. One, if we do eliminate the parameter, it will be, dy dx is a function of x, whereas here we have dy dx as a function of t, of the parameter.